Okay, kids, Mrs. Allen here. Today we're moving into the next unit, and we'll be working with radicals and square roots, cube roots, and so forth. After completing this chapter, you should be able to do all of these things: find nth roots of radicals, multiply, divide radicals, add or subtract radicals, simplify expressions with rational exponents, solve square roots, and all of this stuff that we'll get to. So first I want to start by saying if we're dealing with square roots, we very often want to know what perfect squares are. So you need to be familiar with this first column where it says 1 squared is equal to 1, 2 squared is equal to 4. So if I say 144, a lot of you would identify that as being 12 squared. So the square root of 144 is 12. So I would say that 2 is the square root of 4, 3 is the square root of 9, and so on. And then also in the next column, I listed, since we work with cube roots very much, that we want to say, well, 1 is the cube root of, we say 1 cubed is 1, but 1 is the cube root of 1. And then we say 2 cubed is 8, therefore 2 is the cube root of 8. 3 cubed is 27, so 3 is the cube root of 27, and so on, being able to understand those or get a feeling for some common numbers that you're going to be looking at that, oh, that's a cube root or that's a square root. Then the other part of the language is that we look at roots and we have what's called the index in green, and then we have that little squiggly lines, that's called the radical symbol. That is a root. And then the index will tell you what type of root it is. If it's a square root, if you look down below here, that would mean that the index n is 2, and we would put the 2 there. That would be the square root of a, but we very often just leave it out. In fact, that's what we do. We just put it as the square root of a with that notation. So that's an nth root of a, so to speak. Okay, and so then in this section, we're going to be looking at roots and radicals, and our objective is to find the nth roots of expressions. So again, that expression in the middle is known as the nth root of a, and when you consider the nth root of a off to the right in that pink cloud, the nth root of a is equal to b, then b to the nth power is equal to a. So if I give you a real quick example, if I say the square root, and I'll put the 2 there, the square root of 64 is equal to, let's say, 8, then that is equivalent to saying 8 times 8 is equal to 64. So 8 is the square root of 64, and 64 is the square of 8. Okay? So now there are some things. When n is odd, then we have this expression. The nth root of a has one real root. And that could be either positive or negative. It's always better with a number here. So if you look at the cube root of 8, it's equal to 2. And that's because 2 cubed is equal to 8. And the cube root of negative 8 is negative 2. That's because negative 2 cubed is negative 8. Okay, so inverting the process. Where things go a little bit weird is with even roots when n is even. So one thing to remember about this is that if n is even and a is greater than 0, a has 2 nth roots. It's a positive root, you see it like this, or you have a negative root. I said that backwards, didn't I? I put the symbols in the wrong place. So let me erase those. So it's a positive root or a negative root. So consider this, the square roots of 64 are positive 8 and negative 8, right? So that means 8 times 8 is 64. Negative 8 times negative 8 is also 64. So we say that we have both a positive and negative root of 64. Okay, so which of the following is a real number root? So we look at the index first. It's n is equal to 3. So if n is equal to 3, just keep in mind, is equal to some number, then that means, an equivalent way to say that is that number a times a times a has to equal negative 27. So since this is an odd index, there's only one real answer. So it turns out that the number that makes this true is negative 3, because negative 3 cubed is negative 27. So your answer here is -3, and only -3. One answer. Okay. For B, you have the fourth root. So now with the fourth root, if that's equal to some number A, then that would mean that A times A times A times A is equal to -81. Now, the question is, which of the following is a real number root? Where this was a real number root and it was odd. In this one, if you think about it, A could be positive, right? So if we said A is positive times a positive times a positive times a positive, well, then that would be a positive, right? So A can't be a positive number. How about if A is negative? A negative times a negative times a negative times a negative. Well, that would also be a positive because these two together would be positive and these two together would be positive. Positive times a positive is a positive. So that can't be true. In this case, recall that I said A has to be, if n is even, so here n is 4, and that's even, that means that there's no real root because A, excuse me, I'm using a different letter A here. Maybe I shouldn't do that. Here, maybe I should make this B, but I'll stick with it for right now. Actually, yeah, I don't want that to be confusing to anybody, so let me make this B as I'm making this statement. B times B times B times B. Okay, so I have 4 B's, right? And then we'll just disregard the first one. So in this case, B in this case is not real. And it's because that number 81 is -81. Being negative, it violates the rule. Therefore, B is not real. Okay. Now, in the next one where we have C, the square root of -7 squared, I would simplify. The square roots are a grouping symbol, so simplify the inside first. You get 49. And most of you know, oh, that's 7. So that's a real number. Okay, so this one's a real number. And then going on to the next one, you have a square root. So in this one, n is equal to 2. We just don't put it in there. So the same thing here, n is equal to 2. So where 2 is even, it follows the even roots rule. So here, A is equal to here. A is equal to 49. That's fine. Here, A is equal to -49. So the answer here is not real. This is not real. If I would say B is not real, I could say is equal to B. It is not real because your A is less than 0. Okay? So your answer will not be real. We call these imaginary numbers here. Okay? So take your calculator, you're going to get an error here. And it's because if you consider this, going back to what we did before, if you take, let me move this down just a little bit. If you take this and you say this is equal to, we'll say B, then that means equivalently B times B, because it's a square root, right? The previous one, B above, was a fourth root. So that means B times B has to be equal to -49. And if you reflect for a minute, if it's a positive, if B is a positive, then it's a positive times a positive. Well, that's going to be a positive. And then if B is negative, then it's going to turn out to be a negative times a negative, which is still a positive. So it doesn't work out. It's a total fail. So this is going to be not real either, and you'll get an error in your calculator for using that. So on the next one, we simplify radical expressions. First thing you want to do is know what is the index. N is equal to what? So we're looking right here, right up here. And then we're going to change the radicand. We're going to rewrite the radicand to separate the perfect nth power factors. So now there are a couple different ways that you can do this. You could do it like this, or you could do it like this, 1 or 2. It doesn't matter. Sometimes 2 is helpful for some students, but when you get a power like 9, then you're writing 9 factors out, and it gets to be a lot. So here's what you do. You rewrite the radicand to separate the perfect nth factors. In this case, I need n is equal to 3, so I want to look for the perfect cubes. So in that, I look at 24. 24 is 3 times 8. 8 is a perfect cube. X cubed is a perfect cube. I have to pair off one of the x's because I have an x to the 4th. I have y to the 6th. That's actually a perfect cubed as long as the exponent can be divided by 3, and 6 can be divided by 3. And then we have a z cubed and a z squared is left over. So what we do then, let me get my red marker. Anything that's not a perfect cube in this case has to stay under the radicand. So you see you have a 3, an x, and 2 factors of z. That has to stay under the cube root. If you notice in the line where I have triple factors and 6 factors, what you can do is when you see that you have a factor, 3 factors, that's a cube, a perfect cube, I can extract one of those. So here I can extract 1x, here I can extract 1y, here another y, and then another, I can pull out a z. So notice that what I do is I simplify that up front. Okay, I simplify that to 2xy squared z. That's been extracted or pull out, and that's kind of what I said in step 3. Extract the perfect nth powers. When you do, you can only extract the nth root. Okay, and then the red factors underneath the root have to stay under the root to get your answer. So let's take a couple look at a couple of these quickly. So number 1, you got 32xyz to the 9th. So if I color in green, 8 is a perfect cubed, and z to the 9th is a perfect cubed. I'm going to rewrite those as a perfect cubes. And then if you notice that the red, 4xy, they have to stay under the radical. So I'm going to pull out a 2. I'm going to pull out a z cubed. I'm going to blue there. And then I have the cube root of, you got to watch your cube root and your z cube. Make sure that 1 is inside the root little v thing. And then we have a 4xy that has to stay underneath the root. Okay? So we pull out a z. We pull out z cubed, and we pull out a 2. So you are extracting the cube root of each of the green factors, okay? The next one, we still have two radicals that we have to work with, but they both have the same index. So what we're going to do is bring these two together. So what I did is I'm going to go to blue here. I have the blue factor 2 and negative 3. They're coming out front here because they're not under a root at all. Then I have the cube root of negative 9x squared y to the 4th times. Now I'm going to bring the 12xy over. Let me use a black instead. 12xy. So this is a rule where you can take two roots. If you have, where can I write this? Right here. The square root of a times the square root of b, or the nth root, we better put the nth root here, is equal to the nth root of a times b. You can bring those two together since they are the same root. Now I'm going to leave the 2 times negative 3 is going to become a negative 6, and then I'm going to set up the cube root, and I'm going to look for my perfect square factors. Perfect cube factors, sorry, we often do that. Now, if it's a cube, I can take the cube root of a negative, right? So notice that I have 9 times 12, well, negative 9 times 12. So 9 times 12 is 108, right? And if you need a calculator to do that. Then we're going to take 108, and we want to look at what that is. That's going to be 27 times, 108. 3 goes into 108. So that's going to be 3 times what? 3 times, divide by 3, you get 36. Okay, so now I've got 3 and 36. Well, that's 3 times 12, right? Oh, it's 3 times 3 times 3 times 4, right? So now a lot of people, especially when they're dealing with numbers like this idea, when the exponents are small, you can do this. When they get big, it's just a real pain. So remember, this was a negative 108, so I got to have a negative sign somewhere in this mix, right? Okay, so I've got negative. How do we put the negative on the 4? Because that's going to stay under the radical, okay? No, we don't want to do that. We want to do negative 108. So that's not going to be 3. We're going to use negative 3. Okay, and then we'll multiply that times 4. Okay, so negative 3 times negative 3 times negative 3 is 27 times 4 is 108. So factoring that a little bit, get your calculator out and check that out. So then that's going to be negative 3 times negative 3 times negative 3 times 4, okay? And then I've got an x squared times an x. That's going to be x cubed. That's beautiful, right? Because that's a perfect cube. And you could write that as x times x times x if you wanted to. Then we have a y to the 4th and a y. So I'm going to make that, I'm going to leave that for a second. I'm going to come back to that. Y to the 4th times a y. So now we've got the 12. Sometimes it's a good idea to go through it, and this is, I'm going to wrap up with this one, I think. So it's a good idea to kind of check off what you've multiplied and how you have, okay, I've got this and I've got that, as you're going through your problem that you've accounted for them, okay? And I've got a y to the 4th and a y. So I'm going to play around with that y to the 4th because that's going to be y to the 4th times y, which is going to be y to the 5th, okay? So I'm going to erase this. I'm going to write that as then y to the 5th. And then I recognize that, wait, okay, I can't use a y to the 5th there. So what I'm going to do is I'm going to say negative 6 times the cube root of negative 3, and I'm going to write it as cubed because it's just too long, right? Times 4 times x cubed. I'm going to split the y to the 5th up as y cubed times y squared, okay? I'm going to let you finish the last one. We're going to wrap up with this by extracting the perfect squares, perfect cubes, and there I have my perfect cubes in green. And then remember, what you extract is the cube root of those, and the 4 and the y squared have to stay underneath the radical. So I have a negative 6 times, I'm able to extract a negative 3. Then I can extract an x, 1x, remember it's the cube root of x cubed that I can pull out, and then a y, because I have the cube root of y cubed, and then I'm going to set up my cube root, and then I'm going to leave the 4 and the y squared underneath, and I'm going to simplify. So it looks like I get 18, negative 6 times negative 3, xy, multiplying what's in front of the cube root, times the cube root. I got a long tail on that y I need to fix here. It's a y. So I've got times the cube root of 4y squared. Okay, and there you go. There you have it. Okay. All right, so I'm going to submit this. We'll finish. If you want to try this, you try it on the last one, and then I will see you in class. Okay, and enjoy this video. There's a little gag down here, Metro Math Club open, and I will see you tomorrow. Have a great night, kids. See you when